Hopefully, there's a little bit glitchy still, but anyways. So the idea is that I will quickly mention a couple of basic statistical tests. This is not a statistics class, but like I'm just gonna refresh a couple of very basic tests that we usually do, just to make examples that we're gonna do in Prism. A couple of tips of how to handle statistical tests and plots in Prism, and how to, from that step, to generate figures for publication. Am I muted? Thank you. Okay, am I muted? Where is it? No, audio is on. Okay, from my computer. It's recording from my computer. Okay, no, but what's that? Yeah.
Yeah. Oh, okay.
Okay, so this is the outline. So real quick, this is a classification of the main simple tests that I think is useful for myself that I to just keep in mind when we are testing the association between two variables. If they're both continuous variables, we test correlations, and we're going to talk about that very briefly. If one variable is categorical, the other variable is continuous. If there can be a situation where the observations are unpaired, so we're talking about different groups, or the observations are paired, meaning it's probably the same group followed in time, so with multiple measurements over different time points, for instance. Logistic regression is another situation, depending on what you're going to consider a dependent or independent variable. We're not going to talk about that, but just know it exists. Last situation is where both variables are categorical. We use contingency tables and associated tests that we're going to see in a second. So first, group comparisons. So when, as we said, one variable is categorical, so the group belonging is categorical, and the other variable is continuous. Situations that you can face is either you only have two groups, is majority of the cases usually, and you can use either parametric or non-parametric tests. If there's three or more groups, again, there's parametric and non-parametric options. They just left names of the tests here for you to have an idea of where to, what these names mean and what category they fall in. In general, parametric tests have some assumptions, and smaller data sets often do not meet those assumptions. So usually in most of my papers, I use non-parametric tests because we are studying rare diseases, and we are using a very costly methodology, which is MRI. So we typically don't have a lot of not very big data sets. But if you, for some reason, are working with larger numbers and you can demonstrate that your group observations pass a normality test like Shapiro-Wilk, then you are legitimately allowed to use parametric tests. The counterpart of these, when you have paired observations, the same grid that I showed before, and it's the same variable. So whether it's only 2 time points or more than 3 time points, or conditions. 10 points is just an example. Conditions where the observations are paired, though. So it's not separate groups, separate patients. It's the same group, like followed over time or studied with different methodologies, but the observations are paired across different columns, let's say. Again, you have parametric and non-parametric option, and the tip is the same. So typically stick to non-parametric tests unless you are allowed to use parametric tests. Then we move to when we're assessing correlation between continuous variables, mainly two families, parametric and non-parametric tests. Usually Spearman, I like Spearman's law a lot because it has no specific assumptions and also catches no linear correlations. The only expectation of a Spearman test is that the association is monotonous. So it means that when the x grows, the y grows. Doesn't matter if it's exponential, logarithmic, linear, whatever. It would always catches it because it tests the consistency of the ranks among the measures. Pearson's correlation only works really for linear associations and has some assumptions, has other advantages. We're not going to dig into that very much in detail. The other concept is how to interpret these correlation coefficients. So Spearman's law reflects the consistency of the ranks. This means that, let's say we are assessing the correlation between X and Y. If the ranks are highly consistent, so the raw number is high, so closer to 1 compared to 0, it means that if the X variables has a certain order, so like first highest value, second highest value, third highest values, and so on, the corresponding Y measurements are gonna respect this order if the raw is high. It doesn't mean that they're linearly correlated or anything like that, just that the ranks are consistent across X and Y. R square, which is you can easily obtain from Spearman's from Pearson's R, instead can be read as the percentage variability of Y that is explained by the regression. So already with the Pearson's R, there's a intended linear model that you're running, and R squared tells you how well that linear model that you fit is explaining all the variability in the data. So you can have situations where a linear regression with the Pearson's coefficient has a significant p-value, means that the slope of the line is not flat. But then R squared gives you some more information about how much of that specific line, let's say, describes the data that you're plotting. Let's not get more into detail than this, but just to give an idea. Finally, when you have categorical variables, so no continuous variables whatsoever, you have two alternatives, which is Fisher's exact test and chi-squared. Typically, you would have two categories. It means you have this in the initial plot, I said contingency tables. And we're gonna see contingency tables maybe later, or maybe not. We'll see. If you have more than a category, usually it's more likely that we use chi-square tests, but it's a bit less frequent. Just to give you an idea, just because I have the impression that I'm not explaining this very correctly or very thoroughly. Both variables are categorical, means that not only we have two groups as before, but also the variables that we're studying is not a continuous measurement of a certain entity, but it's just a category. So like, for instance, a good example would be having a contingency table where we distinguish two molecular groups of tumors, and we're trying to assess whether the incidence in the frontal lobe is associated with that molecular type. So you will have a contingency table saying how many are frontal with the mutation, if there's a molecular profile, how many are frontal without the mutation, how many are non-frontal with the mutation, how many are non-frontal without the mutation. General tips, so as we said, because you have these two options, Fisher's exact test has fewer assumptions and usually more suitable for smaller data sets than chi-squared. Chi-squared, I don't know the English. But chi-squared you may want to choose for larger data sets because it could be a little less conservative than Fisher's exact test. In our situations, often I would choose Fisher's exact test. Okay, end of the class. It was just to like recall a couple of general concepts and how to categorize and understand what statistical test falls under what situation that you're going to encounter. A couple of tips of how to make plots in Prism. So general tips and considerations. Plots and statistical tests are two different things. So not necessarily the way you plot the data means that you run a certain test. This is just an basic example, but for like aesthetical purposes or like even layout and space purposes, I decided to plot together these two things, but I'm not analyzing the whole thing together. These are two different groups of patients, red and blue. And in this specific plot, I'm only considering pre and post changes. So this is a paired test and another paired test. I'm not comparing any of these groups across between each other in this specific plot, but I just chose to plot it like this because it was easier and better for layout purposes. Prism guides you to the most appropriate test. So like once you already know a couple of things that we discussed, if you don't remember something, it's pretty easy to navigate Prism and flag what you and get to the actual test that you need depending on the things and parameters and options that you flag. When you're doing plots in batches, I'm going to show you how to do it. You can use the duplicate family function just because it's a bit of a pain to set the tests, the statistical tests the way you want them, and maybe also the graphs the way you want them in terms of appearance of the lines, the ticks, and the dots appearance and whatnot. So if you have to replicate the same analysis on different scenarios, you can just duplicate the whole family and substitute the data. I'll show you how to do it. And then you can use the layouts to just compose the panels for further exporting the plots. Okay, so I prepared the mock data sets. So this is fake data that I made up. It's just to have some examples. So in these situations, we have like patient ID, so these different patients. Patient group, it can be anything. It could be patients that one presented with symptoms, zero, no symptoms, or I don't know, one male, zero females, or genetic mutation, no genetic mutation, whatever you want, just groups. Like there's gonna be a lot of situations when you have different groups of patients. ADC at baseline, so we scan the patient with MRI, we measure ADC within a tumor, for instance, and CBV at baseline, so we measure perfusion at baseline. And then we also have a measurement of ADC at follow-up. Let's say that all these patients underwent a certain treatment or procedure of some sort after the baseline scan, and we have a follow-up MRI with ADC measurements. Forget about the noise. It was for me to create the mock data. Okay, so let's assume we have a data set that is constructed like this. And let's say that as a first thing, we are curious to see if there's baseline differences in ADC measurements, so diffusion measurements, between patients belonging to group 1 or group 0. So we can filter to only have group 1, and we can copy and paste. So in this case, we are comparing ADC to CBV. Sorry, we're comparing ADC of group 1 to ADC of group 2. So we copy and paste. Yeah, see, I skipped the passage because I just need it. So let's say you start from scratch, you have to create a new table. For group analysis, this is misleading. Don't click grouped because it's complicated. It's like for nested analysis and complicated stuff. Like the most basic thing is column. So you click column and you say the second one is fine. So now we have columns and we're gonna say, for instance, ADC group 1, okay? And then we have ADC group 2, of course, at baseline. You can or cannot specify. I suggest that you always rename your data sets because when you start having batches and stuff like that, it's gonna be hard to track what you did. So as concise as you can, but also as clear as you can, always remember that we do plots and write articles, and then we get feedback. We have to change things months after. We get revisions. We have to change things maybe 3 months after you did this. So you have to have things clear enough and documented enough that you are able to recall what you did and possibly make modifications months after. So let's say ADC groups baseline, something like that. Now group 2, I'm going to filter, sorry, not this. I'm gonna filter for the other group. And already, so group is not group 2, but it's actually group 0. Of course, if this has a biological meaning in a plot, I encourage you to write the biological meaning and not just the 0 and 1 coding that you uses for the Excel. Sorry, not this, but this. Okay, so we have 2 groups. As you can see, they don't even match, but that's fine because it's different patients. It's gonna be very rare that 2 groups of patients match in numerosity. So we have our first data set, we do analyze. So as we said, in this case, it would be group comparisons. So you go to the column analysis t-test, non-parametric. So it's both t-test, which is parametric, and non-parametric. They are categorized and grouped together. So you flag what columns you want. Of course, we just have 2 columns, so it's not hard. But maybe if you have data sets with multiple columns, you only want to analyze A and B or A and C or whatever, you can flag it here. Okay. It's gonna ask you a couple of things. This is what I said before. It's gonna guide you to what you're trying to do. Of course, it's unpaired because it's 2 different group of patients. It would be paired if it was pre and post. We'll see that after. And I want to say no, use non-parametric test. You see that between yes, that is unpaired t-test. When I flag no, it becomes Mount Whitney as per the grid that we saw before. Another thing that I highly suggest is to, well, this is a bit, but not necessarily, but a habit that is a good habit in my opinion, is to ask to generate descriptive statistics. So you do this and you see that it automatically brings you to the results with certain p-value of the Mann-Whitney test. And it tells you, the basic results tells you median and median difference, I think, somewhere. Yeah, anyways, the median and numerosity of each group. And then, since I asked to generate descriptive statistics, we also have minimum, percentiles, and stuff like that. This is all useful to generate because in an article, you may have to report some distribution of the data that you analyzed. We go to the graph and we see this is the basic rendering that the graph has. This is not fine because it's like the lines is something that we want to use for paired observations, not for two different groups that have nothing to do with each other. This is like a rendering that assumes that row one has something to do with row one of the other column, but it's not our case. It's just a casualty that patient or row one of a group has another patient of row one of the other group, but they have nothing to do more than row one, row two. So we don't want to see it this way. A lot of people plot histograms or boxes and stuff like that. I like to plot single observations more because it's more informative, as long as you don't have 10,000 observations, which is just confusing. So usually plot the median and the dots. Now you can do any adjustment. So like, for instance, what is this? You're gonna say it's ADC. I usually also put the units. Okay. You do like little refinements so that it looks in a way that you want to publish it. For instance, you could color code G1 and G0 in different colors. That I do that quite often. You're going to change the title to something that is more understandable for a reader, like baseline, diffusion, group differences, or something like that. Okay. When you start changing, okay, if you open this plot, it lets you change the symbol size and color and whatnot. I'm just gonna let you experiment with that. If you can change one group at a time, or you can change all data sets. For instance, if I want to make all of them squared instead of circles, I can say change all, and I'll just change that and it will apply to all of them. Some journals charge for figure colors, so be mindful of that. Some figures are necessary to be in color, so you'll just do in color. Otherwise, if you just want to color code different groups, I often use gray too, just to show that it's different groups, but you don't get charged. So this is an example. Another thing that I typically do is you can use these tools to add to add like p-values differences. It's a bit lagged through screen sharing, but I guess like you adjust it the way you like it. This is horrible. It doesn't even, okay, let's pretend it looks fine, okay? And you can use the text panels to say whatever level of significance, or even write down the p-value if you prefer that way. Okay?
You can also make it print the p-value. So you right click.
Oh, you can?
Yeah, it's
Okay, let's do it. So with the text box, okay.
Oh,
Right click here.
right click here, and then you set insert info or analysis constant. Sorry, I don't.
Do it. Oh,
And then it get sorry, I cannot navigate from here.
okay. What
Then can you go to the
here?
analysis that you did, expand it,
Okay,
and then the test, and you can
interesting.
select whatever variable you want.
Oh, okay. So if you want to change it after, it's gonna automatically change.
And if you copy the family, it's gonna translate that
That's
information.
good. That's good to know. See? Where did it print it?
It usually puts
Oh, okay.
and then you move it wherever you
I
want.
see, I see, I see. I didn't know this. So yeah, I mean, you may wanna adapt it because 4 to the e to the minus 0
Yeah.
side. It's not very pretty.
Here's the value, so you would have to put the tag in a text like
Yeah.
p value equal and then
Mhm.
y.
Okay. Let's just leave it like this, okay? So I mean, you would have to add p plus, yeah. Beautiful. Okay, unreadable or beautiful. Okay, let's say we're satisfied, we like it this way. Now, we did a couple of adjustments, say of the graph, we changed the colors, we have all these things. So since we're gonna do the same analysis with CBV, because we want to see if there's perfusion differences, the fastest thing is to double click on the data and say duplicate family. So this is going to be CBV groups baseline. Of course, you have to manually change the data after that. Say this is CBV group 1, and this is CBV group 0. Okay. It's a good habit to erase this immediately because otherwise you start doing something else and you forget and you just propagate wrong numbers. So this we already selected by group 0, so we can copy and paste CBV group 0 values. And now we're going to do the other group. Okay. So this is not significant. So it means there's no significant difference. This, again, it copied the same layout as before. So this is why we see ADC. So you want to change it to RCBV. This is a bit unclear, so you may have to, I don't know, change it. You can angle it instead of having vertical. Another thing, you can just make it smaller. It's probably easier like this. Now this P is in the way, this is a bit in the way, so maybe you want to change the range of that a little bit. So you can go y-axis instead of automatically determine, you can go -1 if you like it. It doesn't, I'm just making an example. And you can say apply so that you have this open, and you can keep changing things until it looks good to you. So of course, let's remove this. And this you can bring up here. Something like this, okay? Now, some other things. Let's start from scratch. And now we want to see if there is a difference between pre and post ADC values, right? So column again is the same, is the same structure as before. Now we're gonna say ADC changes, pre-post. ADC at baseline. Now we need to select all groups. ADC at baseline. And ADC at follow-up. See, times 0, ADC times 1, or whatever you want to call it. Now, to do the analysis at this point, you start off as before, but the difference is now the observations are paired because it's the same subject before and after. In case it can happen that on longitudinal data you have missing data, right? It can happen that one patient only had pre and no post because that was lost to follow up. Prism, if there's a empty cell, Prism is automatically gonna exclude that from the observations. Use non-parametric, so Wilcoxon, as we said before, it's barely significant. So there is a trend I mean, there's a significant difference, even though maybe not strong as before. The median, when you use paired data and you look at the median, first of all, I forgot my good habit of creating descriptive statistics, and you should do that. But median tells you the median of the differences. So this means that it's significant, and the general behavior is that there is an ADC increase after the whatever treatment that these patients received. So for this plot, you can, so first of all, we like that there's lines because these are paired observations. Fusion measurements, whatever. Fusion over time, something, whatever that explains what you are doing. So times 0 times 1. Again, they're too large because they touch each other. This is ADC. Another thing we can do actually, whatever. So these actually would be time points or something. Another thing you can do, so for instance, the second group should be gray, right? You can use the magic wand. The magic wand serves to go retrieve another plot that you did recently, not only necessarily in this file, but see it's seeking also other files that I have. Once you select your target, your reference, let's call it, you can select what you want to mimic from that other plot. So for instance, graph origin appearance, yes, because it's like ADC to ADC, that's a good idea. Reagent X2. And it's gonna show you how it's gonna change it. So it got rid of the lines, and I don't like that. So I guess I have to unflag this. Yeah, but if I unflag this, it's gonna also get rid of the colors. Let's just do this for now, and then I think I can repristinate, yeah, appearance before, after, and I can go here and do lines. It's not letting me. Anyways, so in this case, it probably would just simpler to change the second one to gray here, or whatever shade of gray you want. Okay, this or other type of gray, whatever. And these are too thick, they're ugly. Okay. So this gives you an idea of which subject increased, which subject decreased. Again, I would add the P and whatever. You can also add what the median of the differences is, and so on. Last thing we want to do is to see if ADC and CBV correlate, just for the sake of showing a correlation. In that case, would be new data table. XY is what you want to flag. Single value of Y for each stop point should be the correct one. So now we have X and Y. In this case, it doesn't matter, right? Because like you're just assessing a correlation between two variables. In other cases, you may want to be particularly mindful of what you want to put on X or Y, because like X should mean that's the independent variable and Y is the dependent variable. So we're gonna call it ADC CDV correlations. And let's say we have no idea whether it's gonna be a linear correlation or not. Let's say we're gonna use Spearman. So when you flag the correlation, so you see there's a correlation option for linear correlations with Pearson. You can also flag simple linear regression instead. But let's stick to correlation for now. So go to correlation, and it's going to ask you if you want to use Pearson or Spearman. In this case, I want to use Spearman. So this means that the ranks are maintained, and the Spearman raw is minus 0.5. So it means that there is a negative correlation of the ranks. So this is what the data looks like. And you can, if for some reason you want to, you could also fit a linear regression jot down the measurements of that are related to the linear regression for instance Pearson or whatnot, but no one prevents you from also reporting a Spearman raw and discussing both things. Okay, I usually don't like. Well, it doesn't matter. I think it's getting late. Let's just say this is RCBV. And this is ADC. And you may also want to report a row. The regression line you have to fit a regression. So let's just say we wanted to do that. Analyze simple linear regression. Because in this case we just ran a Spearman, right? And you want to show the confidence intervals because Ben wants to see the confidence intervals. Yes. So in this case, it shows a line with confidence intervals. And well, in that case, if you're showing this at that point, I will also report an R square probably, which is here, R square 0.22. Okay, so now let's say that this is pretty ugly. So frame and origin, lower left. Okay. Yeah, I mean, if you like it this way, you can change the sizes of the axis as you wish. So usually when you say you're done with all the plots that you want to show and you want to organize them for a combined figure, for instance. Let's say that, so you can click the layouts and select whatever layout you like the best. So for instance, here I would show ADC and CBV. I already caught an error because it says diffusion, but it's perfusion. So you'll go back and change it to perfusion. Of course, this is the native graph, and whatever you change on the native graph, it's gonna show on the layout. So see, it did correct perfusion. And then this and this. Let's say we are satisfied with this. You can arrange the size of the plots relative to each other, whatever you want to show, maybe like this, whatever you want to show, whatever way you want to show. Let's just do it for like this for this time. But usually like you would probably try to squeeze them a bit more because like all this white space is unnecessary, but for the sake of brevity now, we're just gonna accept it as it is. And always remember to put A, B, C, D, because like when you write a caption, you don't have those as a mess. Now that let me get back to this. Okay, so let's say we saw how to use layouts and how to do a couple of analyses and stuff, and to change things around and use the families. For the generation of figures, so for presentations and drafts of the article, in my opinion, high resolution images are not requested, and actually they're heavy. And if you have, say, a Word document with all your article and you have high resolution images, then it becomes super heavy to send via email, or when you open it, it's slow and stuff like that. So I usually don't do that because it's useless. Just maybe if you're doing a presentation at a conference and you know the screen is going to be large, try to magnify whatever screenshots you acquire to make sure that when it's stretched out, it's decently, the resolution is decent. For an article, it's a different matter. There are specific requirements for resolution. Usually use a TIFF format and you'll never go wrong. Like different journals will accept different formats, but TIFF is always accepted. In terms of DPI, images like MRI images, 300 and more is fine. Also, we have MRI images, then the resolution of the MRI images is like 1 by 1 by 1 millimeter at best. So it doesn't matter that you have 1200 DPIs because like you would be upsampling something that is, but the, okay. Whereas for plots and line graphs and so on, you should go as high as you can in terms of resolution. And we're gonna see that in a second. The procedure, there's 1,000 different ways that you can do it. I'm just gonna show you how the strategy that I developed over time to do it, it's the one that works best for me. So I try to stay in the PDF format as long as I can because PDF has this property that it does interpolate. So like the more you zoom, the more it's going to interpolate line graphs or text and so on. And just at the final stage when I'm completely sure about the figure, then I convert to TIFF. For line plots, for instance, this, you can just generate PDF figures from the layouts on Prism. If you generate with Python or MATLAB, always generate them in PDF is my advice rather than PNG and other stuff, but that's my preference for the same reasoning that I explained. For MRI images, it doesn't matter. You can just take a screenshot and stuff and just populate a PDF. Sorry, not a PDF, a PowerPoint or Keynote, whatever you use, because you're going to use the PowerPoint and stuff to add text. Whenever, and link to the MRI resolution matter that I was mentioning before, when you will export PDFs from PowerPoints with MRI images, you see that when you zoom a lot into it, the letters are well defined because the PDF format does interpolate every time that you zoom in. But you'll see that, of course, the MRI image is not going to increase the resolution because it's the pixel resolution that the MRI method has a constraint for. And then there's gonna be possibly hybrid figures where you have line plots and you also have brains and stuff like that. And what I usually do for that is that I generate a Prism PDF or a Python PDF for other plots. Then I put everything in a PowerPoint. Then I regenerate another PDF, and then I generate a TIFF from there. So, and I use GIMP finally at the final stage to convert PDFs to TIFFs. I'm just gonna show you how I use that. So for instance, we got to this scenario. I go File, print, just this sheet, save as PDF. Call it like temporary figure plots, whatever. I think I have to. Who knows where I put this data? Documents. Here. Okay, so I have a temporary PDF, and then let's say that, well, I have a test figure here. Okay, so let's say this is the PowerPoint that I wanted to use to generate my figure. As you see, I changed the setup so that it's close to like a A4 vertical, just because in journals you can have a figure that is as big. So I try to work in that format. So for this situation, I'm going to can just drag and drop whatever PDF you generated and regulate the size, whatever you want. And then let's say this is one of those hybrid figures where I also want to add images of some sort. For instance, well, this is very small. For instance, I don't know, like this figure, just very random. Okay. So now you compose your figure however you want it. So possibly it's gonna be prettier than this that I just did here. But the concept is that now we have this is all a PDF format. This is a screenshot that I did. So we re-export whatever file. You can add text, you can add A, B, C, D, E panels and all that and all that. After that, you again do the same thing. So you, at least that's how I do it. You save it as a PDF, say test figure, and then and then once you have a final PDF that you are satisfied with, what I do is I open with preview. Of course, it's gonna open in another screen. I open with preview, I crop to the only the part of the PDF that I'm interested in. Be as tight as you can because in the journal it's gonna be surrounded by white anyways, so it doesn't matter that there's the tighter the better. And you can crop it and you save it the way it is. So this is what the final figure is gonna look like, but now the final step, because we're still in PDF. Where's GIMP? But with the way I try it, you cannot set the DPIs, or like you can, but then it doesn't work. So that's why. But maybe works in your case. Where is GIMP? Okay, so GIMP is here. GIMP is free, and you can download it for free. So let's say, oh my God, so glitchy. Okay, so let's say this is the final figure that we like, that is cropped the way we liked it. You drag and drop in GIMP, and this is where you pick the DPIs. So this is mainly line graphs. So I would try to keep it 1200 at least 600. There's always like a trade-off, right? Like you can go as high as you want in resolution, like 1200 if it's only line graphs and plots. But if you start having images in there, like that's gonna make it too heavy sometimes for the size cap of some journals. Let's just say 600 for this case. So the cool thing is that you set the resolution the moment that you import it. And after you do it, I mean, GIMP can be used almost as a Photoshop to change, like adjust things and stuff like that. I've never tried that, so I don't know how to do it. That's why I use PowerPoint. But so I just use it for this passage of dragging and dropping and then exporting at the correct resolution. If you click export as, yes, sure. And then test figure, and then you have to select the type of format. So in this case, it would be a TIFF format. And always click LZW as a compression, because otherwise the size is gonna be incredible. But LZ is fine. It works great. So after this, if I didn't miss up anything, we have a TIFF file that is 1.6 megabytes, so definitely acceptable. And if you do this, it's gonna tell you, see here, always check this 600 by 600 resolution. So it looks correct, it's in TIFF, and it's the right resolution. So this is a figure that you can use for submission. That'd be all. Questions? Okay. Okay. Of course.